page 402 at the top. If you want to color code it, it's kind of interesting when you color code it because there's three variables, b, a, and x. But what's terribly fascinating about this formula is the letter A only appears on one side of the equation and not on the other side of the equation. The x is on both sides, the b is on both sides. But the a is only on one side. And this is not on your formula sheet. You either have to develop it or memorize it if you want to use it. It is on the wall over there. So what this means is we could take something like log 3 of 7. I have the left-hand side here, log 3 of 7, and when you switch it to the right side, it allows you to pick anything you want for A. So I'm going to pick 10. Or I could pick, I'll do it in orange here, E. And log base E, that's just the natural log. Or you could pick 355,802 if you wanted, and change the base. Now it's most helpful to use a base of 10 or a base of E because every calculator has those buttons, the common log and the natural log. But not every calculator has a base 3. And when you get to your exam, you're not going to be using your graphing calculators, you're just going to be using scientific calculator. So then you might need to know how to do this. And you could get questions like this one. It says combine as a single log. So this is a simplify. And it's important to recognize that log 7 divided by log 3 is not the same, right? If you have dividing inside of a log, there's a log law that says you can subtract. But if you have a log divided by a log, the only thing you can do is say, I have the right-hand side of this formula. I can change it to the left-hand side. And if I change it to the left-hand side, whatever A was just disappears. It just goes away. So in this question, to combine as a single log 7 over log 3, I could change to log 3 of 7. And this common log, which had a base of 10, that 10 just goes away. And then I have log 3 of 5 plus log 3 of 7, and since the bases are the same, adding is the same as multiplying. So with that, we're ready. Is everybody done? Okay. We're ready to go to example 1. Now it says approximate to the nearest thousandth. That means that you need a calculator. So we could just type this in for a calculator, but one of the things that we could do is we could use your change of base theorem to change log 5 of 50 to log 50 over log 5. That makes it easier and faster to type it into your calculator. So I can do log 50 divide by log 5 and find out it's 2.431. If if you were estimating it, since you know 5 squared is 25 and 5 cubed is 125 from your powers chart, it should make sense that your answer gives you something between 2 and 3. And same thing in B. I could use the change of base theorem to make it equal to log 6 divided by log 8. Go to my calculator. And I get 0.862. It kind of makes sense because if I had 8 to the 1, it would be 8. And 8 to the 0 is 1, so it should be somewhere between 0 and 1, and we got 0.862. Now, the change of base theorem is actually really, really easy to show why it works. And I'm going to do that for you right now. So I'm going to say, if I let x equal log 5 of 50, I could change this to exponential form. The base is 5, the exponent is x, is equal to 50. And I get an equation. And when you have an equation, what you do to one side, you do to the other side. So you could square root one side, then you'd have to square root the other side. Square rooting is a function. So what we're going to do is we're going to use the new function we just learned, which is logarithms, and we're going to take the log of one side, and then we'd be forced to take the log of the other side. Now, if I take the log of this side and the log of this side, does it make sense that I could pick any base that I want? I'm going to choose 10. But I could erase those 10s and make them 30s, or e's, or any number I like. It wouldn't matter, because they're all functions. You could take log base 10 of both sides. You could take log base 2 of both sides. You could take log base pi of both sides. Those are all possibilities. But if I do this, I'm like, hey, wait a minute, isn't there a log law with the exponent? I could bring that exponent out in front. And this is the powerful thing about log laws. Because I can bring that exponent out in front, and I don't have to write the 10 because it's the common law. Are you okay with that? Now, it's x times log of 5, and log of 5 is a number. So if I wanted to get x by itself, all I would have to do is divide both sides by log of 5. And now I have that x is equal to log of 50 divided by log 5. And what did I start with? We just proved the change of base theorem. We just started with one and made it equal to the other one. In fact, I chose 10s, right? I'll add them in again. But I could have done 101s. And it wouldn't matter. This part, right, in your change of base formula, which was the a value, you could pick anything you wanted. Because what you do to one side, you do to the other side. Now, the base of 101 would be kind of pointless because that's also hard to type into your calculator. And so you started with something that's hard to type into your calculator, and you changed it to two new things that were hard to type into your calculator, so it just takes longer than you started with. And then you could change those to new fractions and have new change of base theorems and make it really, really, really complicated in the end. But what we're doing here is we're taking the log of both sides, and this is going to be really important in 5.7 and 5.8, because you now have the power to solve any exponential equation. You have 3 to the x equals 7. Take the log of both sides. Oh, I have a log law that says I can throw this out in front. Curious what x is? Well, you can get it by itself. It's just log of 7 divided by log of 3. And you've now taken the equation that's not on your powers chart and solved. And so this is the reason we're practicing all of our log laws is so that we can get to that point, and we'll be doing that in 5.7 and 5.8. Okay, questions for practice on this one? All right. 3, 4, and 5.